This afternoon's session is going to focus on information from remote sensing through spectroscopy. We've heard a little bit about this scattered through the talks this morning, but this afternoon's session will be much more focused on spectroscopy and the link directly to observations. So I want to give a kind of physical reference point for the chemists in the room. We've heard some of this morning as well, but I'll walk through it all in one concerted effort. So this is the Eagle Nebula, which is a region of gas and dust in the interstellar medium, which unfortunately is not showing up very well on the screen. But this was one of the very first Hubble Space Telescope images that was produced. These are talons in the Eagle Nebula that are interstellar clouds, and these little wisps out on the edges are regions where new stars are forming. And so if we walk through the different physical conditions in a region like this, we can start with Earth at sea level as our reference point, 10 to the 19th molecules per cubic centimeter and 300 Kelvin temperature. The distance from us to the sun is 1.5 times 10 to the 11th meters. One of these edges of the box of the Eagle Nebula here, one talon, is about 10 to the 16th meters. So that spatial scales are immense compared to even our own solar system. If we look at the gas between the interstellar clouds, the diffuse interstellar medium, we have about 10 molecules per cubic centimeter, and it's about 50 Kelvin in temperature. If we go into these dense dark clouds before stars form, it goes up to about 10 to the third molecules per cubic centimeter, but the temperature goes down to 10 Kelvin. So it changes the chemistry compared to what we would expect in a laboratory on Earth. And then if we go in these regions of star formation, or hot cores as they are called, where the new star has started to warm up the gas and dust around it, but a solar system hasn't completely formed at that point, now the density goes up to 10 to the 7th, and it's about room temperature again. But even at those densities, the timescales for chemical reactions are incredibly long, and so we need interactions like ion-molecule interactions. We need grain surface reactions with radicals, which we heard a lot about this morning, to be able to drive the chemistry of space. So if you look at this picture in terms of how stars are born, we start with a cold dark cloud. It collapses gravitationally. Eventually a rotating disk, like Catherine Walsh talked about this morning, forms, and from that disk we can form planets, and then eventually a mature solar system like our own. And so what we really try to study in astrochemistry is how the chemistry changes as the physical conditions change through each step of the star and planet formation process. And to do that, we use remote observations. We heard a bit this morning about radio observations and a bit about infrared observations of molecules. And so for the chemists, I want to kind of, ground us in terms of what it is that we're looking at and what you would have learned as an undergraduate chemistry major doing a lab in analytical chemistry or physical chemistry. So if we look at visible transitions, we're looking at electronic transitions. So the Hubble Space Telescope, most of those images are actually composites of different wavelengths looking at atomic transitions in the visible or the ultraviolet. In the infrared, we see molecular vibration, so we see stretches and bends. These are kind of, to chemists, the fingerprints for identifying molecular functional groups. But as we saw with some of the talks this morning, it doesn't give us the specific detail we need to be able to sort out exactly which molecule it is. It lets us narrow it down in terms of the chemistry, but we can't always detect directly from that exactly which molecule we're looking at. If we look at rotational transitions in the radio, the microwave, the millimeter, the submillimeter, these transitions are actually very high resolution, as Mike McCarthy showed this morning, and these are specific to the structure of the molecule. And so it actually gives us a fingerprint of the molecule that we can compare directly to laboratory studies and to theoretical models of the structure. And the only caveats here are that the molecule be in the gas phase so that it can freely rotate, and that it have a dipole moment. And so it's from radio observations that most of the molecules in space have been detected. And now we're starting with the telescope technology that we have available, move in the direction of vibrational studies using infrared wavelengths to try to get at more complex chemistry in environments that can't necessarily be probed using rotational spectroscopy with radio telescopes. So if you look at the Milky Way and you look at it in different wavelengths, we can start out here. We have molecular hydrogen in the radio. We have infrared. We have mid-infrared. And as you move towards optical, you can see different components of the clouds and the gas and dust in the Milky Way. And so we can compare all of these images and try to understand how the different wavelengths tell us different molecular information about the universe. As I said, most of the molecules that have been detected in space have been detected through their rotational transitions, and these 3 telescopes have basically revolutionized the field in the last 10 years. These are the Herschel Space Observatory, which was a 5-year mission. It ran out of cryogens for its detector, so we can no longer use the observatory, but it was a space-based far infrared observatory. SOFIA is a NASA telescope that actually flies in the back of a plane. So they cut a hole in the plane and point the telescope out the back so it can fly over most of the water in the atmosphere and do observations that way. And of course, we've heard a lot today about the ALMA observatory in Chile, 66 antennas working together to take both spectra and chemical images of space. All 3 of these observatories work in this region called the far infrared. To astronomers, to chemists, it would be terahertz if you want to talk about frequency space. And I've got the scales here. So we have terahertz, we have wave numbers, and we have wavelength in millimeters down here. And this is the region where small molecules that rotate have their fingerprint signatures. Large molecules that have low-lying vibrational modes show up in this range. And we also see fluxional behavior, so functional groups rotating or inverting that lead to complicated spectral patterns. So from this, we really can go to the lab, take a spectrum, go to the telescope and take a spectrum, and have a direct match between the two, and we can quantify it using the Beer-Lambert law in most cases and pull out densities and temperatures from those observations. So if you take a look at Orion, this is what Orion looks like when we look up in the night sky. The fuzzy spot in Orion's sword is the Orion Nebula. If you take a spectrum of the Orion Nebula at these radio frequencies, you end up with something that looks like this. I think Ted's spectrum from the Herschel Observatory was shown a couple of times this morning. Higher frequency, same concept. Thousands and thousands of spectral lines. We have a handle on about 75% of the intensity and about half of the line density, but the other half of the lines we cannot assign to anything that is available in the literature that has been looked at in the lab. And so we really need fundamental laboratory studies that go and measure these molecules of interest, and we need rapid ways to analyze a lab spectrum and an observational spectrum to be able to sort out this complex mixture chemistry. So for the chemists in the room, if you're worried about complex mixture analysis in industry and synthesis in the lab, astronomers and astrophysicists have the same problem, just with remote observations instead of a sample that we can hold in a flask. If we do imaging studies, like with an interferometer like ALMA, this was actually from the Karma Observatory, which was an ALMA predecessor, you can start to get contour maps of molecular emission that tell you not only the temperatures and densities of the molecules, but also the distribution spatially of the molecules. So these are contour maps like a map you would use if you were hiking. You can see the concentric circles here. And so these contours tell us where the emission peaks in the object. In this particular set of images, the colors map out the temperature that was measured using methanol. And then the contour maps actually show the emission of methyl formate and ethyl cyanide. So if you image the Orion hot core region, this is what it looks like in molecular emission. And you can see that the two molecules have very different spatial distributions. And so from this, we can start to sort out based on the dependence on temperature, the spatial scales of the molecules, and the regions that they show up in, what sort of chemistry might be driving their formation, and what sort of mechanisms could explain this sort of emission. Now with ALMA, we can actually start to zoom in on these star-forming regions and get very detailed images. And every single pixel in an ALMA image has a broadband molecular spectrum hiding behind it. And so we can actually now sort out the distributions of dozens of molecules in any one observation. The challenge is being able to assign and analyze all of that information. It's overwhelming. I think Mike said this morning we went from a data poor to a data rich field in just a couple of years. And so this is something that we really have to get a handle on as molecular astrophysicists and laboratory astrochemists. So the really great thing about ALMA is because it has so many dishes and such a large scale in terms of its baselines, we can narrow in and look at very high spatial resolution at objects that we could not resolve spatially before. So we can look at accretion disks, we can look at planet forming zones, we can start to sort out the chemistry in these very small regions of space. So this is an image of a snow line. Catherine mentioned this morning. This is where molecules freeze out onto the dust in a disk. And so you can actually look at the snow line in this disk and see that it compares to the orbit of Neptune in our solar system. And so ALMA has really transformed the field in terms of being able to sort through these things and start to understand the chemistry and how it changes in these very compact objects that we could not study in detail before. And this image you've seen, I think, at every talk so far. These gaps, we think, are where planets are forming in a protoplanetary disk. And so ALMA can start to probe the chemistry as active planet formation is happening in a disk. So this is really where the field is going now. Interstellar chemistry is starting to move into the range of planet formation, and then eventually we hope link to observing exoplanets outside of our own solar system. So I want to talk just briefly, because we have speakers later on in the session that'll go into much more detail than I will, but the big questions in this field are, where are the planets in other solar systems? How big are they? Are there any that are like Earth? Are there any that are showing up in the habitable zone, which is the region where there can be liquid water at the surface of the planet? And what can we learn about the chemistry of these planets through observations through spectroscopy? And so if we take a look at what can happen with the James Webb Space Telescope, which will launch in a few years, we hope, right, Stephanie? The James Webb Space Telescope will give us access to high-resolution infrared observations of many different types of regions, but one of the most exciting things for astrochemists is to start to look at the chemistry of exoplanet atmospheres. So we can actually start to look now at possible biosignatures like water vapor, the presence of methane. We can learn all sorts of chemical information about the atmospheres of these planets, and we can start to sort through that exoplanet chemistry and understand how that links us from star and planet formation to an Earth-like planet, to a solar system like our own. So our speakers this afternoon cover the whole range of star and planet formation. We're going to start with Ted Bergen, and he's going to tell us about where the carbon is in the solar system. And then Ilse Cleves will tell us about chemistry and disks of gas and dust. Sarah Horst will tell us about chemistry of planetary atmospheres and what I'm guessing what we can expect from JWST. And then Jonathan Fortney is going to tell us about planetary evolution. So we'll start with Ted.